Welcome back to the class of differential equations and matrices. And we are in section 3.6. It's about the basis and the dimension. But anyway, we just started a new concept. It's a linear combination and the span. And now we know, I suppose we know roughly how the span of two vectors would look like. This span, it is a plane in the three-dimensional space. And also we realize sometimes when you add a vector there, it really will not affect the span. So in this case, adding this vector w here, it's not going to affect the span. Those two spans are the same. And then in part B, we added another vector. And then actually we realize this new vector, it is linearly independent to those two original ones. They are not the same. They are not the same. They are not related. Okay, so we figured out this new span, the span UVX, it does cover the entire three-dimensional space. See the thing? A span could be the entire vector space or could be part of it. And indeed, we didn't mention the span, it is a subspace of the original vector space, okay? Because the span it is closed on the scalar multiplication and vector addition. And the next example, let's take a look. We said that, well, vectors usually we consider two-dimensional, three-dimensional vectors. But anyway, indeed, in mathematics, we can consider any object as a vector. So could be functions, And so next part, what we are having here is we are having a set of functions. Set of one, it is t plus 1, t squared plus 1, t squared minus 1. And we want to identify the span of the set. And in particular, somewhat we are hoping this span will cover the entire vector space of P2. Anyone remember what P2 is? P2, it is the set of all polynomials of degree 2 or less. The word or less, it is very important because otherwise it will may not form a vector space, okay? So here is what I did. Because we want to check if all polynomials, any polynomials of degree 2 or less could be written as a linear combination of those three. So I just said, well, this is in general any second degree polynomial, right? And also it could be degree 1 if we set the coefficient as 1 here, as 0, a as 0. And also in the case A and B both at 0, it could be degree 0, a constant. So basically it's just true. Any polynomial in P2 can be represented in this fashion. And then we want to see if this polynomial can be represented as a linear combination of those three functions. So I just said that maybe I assumed it is yes. The vector can be written as a linear combination of those three functions, which means we really need to figure out the constants C1, C2, C3 if all possible. Okay, so here is what I did. Because I understand I'm really comparing with two polynomials, polynomial of degree 2 or less. So what I did here is the linear combination of those three vectors, and it is arranged according to the like terms, Okay, and then basically this is polynomial of degree of 2, that is also polynomial of degree 2. I want to match the corresponding coefficients. So C2, C3 equals A, and then C1 would match to that B, right? And then the actual constant part comes from those three, C1 plus C2 minus C sub 3. And then, well, I'm having three equations. I believe I did it correctly. And also, it will be very helpful if you arrange those three. You don't need to, in general, you really don't need to actually solve these three. I guess in this case, I think it might be just easier just solve them directly, okay? Solve them directly. So what I'm trying to say here is you may want to use a matrix representation for the system. So we do have a coefficient matrix times those unknown quantities C1, C2, C3. They must be the right-hand side. well, the vector, okay, I mean the polynomial of degree 2 in last. Okay, that must be the coefficients are arranged in a vector form A, B, C. And then one thing I just realized here that you want to take a look if you are convinced. I'm saying this coefficient matrix is invertible. There are many ways to say a matrix is invertible. I would say probably for our class purpose, maybe the easiest way is just to check with the determinant. So I checked with the determinant, I'm seeing the determinant is not a 0. So I'm saying for any polynomial of degree 2 or less, we always can find out a unique set of solutions such that this polynomial, okay, this polynomial can be written as a linear combination of those three. So indeed, the answer for exercise 5, it is just true. The span of the set, it is the collection, the vector space of P2, which is the vector space of all polynomials of degree 2 or less. I guess maybe take a break first. Thank you for watching. I'll see you next time.